This is the last of our respiratory system PowerPoints. This one is on respiratory gas exchange, which begins on page 77 of your course pack. And here we're going to talk about internal and external respiration in a little more detail. First, I'd like to give you some background information that's not in your course pack, just to kind of give you an idea of what's going on. The air that you breathe is a combination of gases. You'll notice in this image that the major gas in the air that you breathe is nitrogen gas. That one is N2 at 78% of the air that you breathe. You'll notice that oxygen, only about 21% of the air that you breathe. And then we've got argon, H2O makes up a little over 1%, and then carbon dioxide makes up less than 1% of the air that you breathe. Interesting to note, vast majority of the air that you're breathing in is actually nitrogen gas. So gases move throughout the air and throughout our body simply by diffusion. And to review this concept, it is a process by which molecules move from areas of high concentration to areas of low concentration. No energy is needed for diffusion. You may recall this is a passive transfer process. All right, so this chart is from your course pack, and you'll notice that nitrogen gas is 78% of the air that we breathe. Reading down this percentage of atmosphere column, oxygen is 21%, there's CO2 and oxygen, water rather, at the very bottom. We're going to concentrate on oxygen and we're going to concentrate on CO2. We're not going to look at nitrogen gas. That's only important if you happen to be a scuba diver. All right, so you'll notice outside the body, this is in the air that you breathe, the partial pressure in millimeters mercury of oxygen is around 159 millimeters mercury. I'm going to move across here. I'm going to go this way. All right, so once that air moves into your respiratory system and makes its way to your alveoli and your pulmonary capillaries, that level mixes with water vapor and actually drops a bit, about 104 millimeters mercury. Notice high concentration, a little bit lower, and then when we get into the arterial blood, we're looking at about 80 to 100 millimeters mercury. That's what we consider to be a normal partial pressure for oxygen. So let me explain this term partial pressure. You notice it up here at the top of this slide. Partial pressure is the pressure exerted only by oxygen as part of a mixture of gas. So we know that, a good portion, about 78% of our air that we breathe is nitrogen gas. You'll notice this magic number here, 60 or lower, is considered hypoxia. You'll want to know these numbers. 80 to 100 is normal. Less than 60 is considered hypoxia. That is a far way to drop before you end up having a problem. All right, and then finally, let's talk about CO2 on this chart. I'm going to work you in the opposite direction. In arterial blood gas, 35 to 45 millimeters mercury is normal. We know that already from our previous conversations. Less than 35 means there's not enough CO2. You head into alkalosis territory, and more than 45 millimeters mercury is what we consider acidosis. So we know that CO2 is loaded into the bloodstream at systemic capillaries. That CO2 travels to venules and veins, taken back to the heart, eventually dropped off at the lungs by way of pulmonary capillaries, and then we exhale out that CO2 into the air that we are breathing out. You'll notice that by the time you get outside the body, we're looking at less than 1% of the air being made up there of CO2. So as long as we've got these pressure gradients, then air will move into and out of our bodies along these gradients. All right, I'm going to box off this set of numbers here. You will want to know those numbers for the test. Let's review external respiration. We briefly talked about this earlier in this chapter. We know this is a process that occurs in the lungs. It is simply diffusion, and it's a way for blood gases to move into the blood or out of the blood. All right, so back when we talked about this earlier, we know that oxygen is loaded. That means it's placed into the bloodstream from the air. We know this process occurs simply by diffusion, so oxygen moves along a pressure gradient from alveolar air into pulmonary capillaries. Carbon dioxide is unloaded. That means it's removed from the bloodstream and placed into the air. It's actually moving in the opposite direction, so you exhale out the CO2. You may want to check out that YouTube video link at the bottom of this page. So let's repeat. Here we're looking at external respiration. Let's just make a note. This occurs in the lungs. Right here you have a pulmonary capillary. And it surrounds an alveolar air sac. I know it's labeled. Let's go ahead and label it again. All right, and we're looking at a gas exchange. The reason it's called external is because it occurs between you and the outside world. Here's oxygen. Here it is being loaded onto hemoglobin. And of course, when oxygen and hemoglobin combine, we form what's called oxyhemoglobin. Do you recall what color oxyhemoglobin is? You might recall it as bright red. All right. Recognize this equation. We looked at it earlier. We actually had it running in the opposite direction. We showed it going that way. But now we're running it in reverse. We are taking bicarbonate right here, and we're making CO2 out of it. And that CO2 is what is diffusing into your alveolar air sac, and then you exhale that out. So get rid of the CO2. You exhale that out. What are we doing with that oxygen? We're taking it for a ride, ultimately ending up with our systemic cells and tissues. Now, internal respiration is also a gas exchange. It's just in a different location. You'll notice this one is between systemic capillaries and cells and tissues. Again, the gas exchange is simply by diffusion. This time, you'll notice oxygen is unloaded into cells and tissues. We're going to use that to make ATP by those mitochondria, while carbon dioxide is loaded into the bloodstream for transport back to the heart. All right, so let's label this one. Internal respiration occurs systemically, so that means all over your body's cells and tissues and surrounding capillaries. Right here is a capillary. This could be anywhere in your body that is supplied by capillaries. And here are your systemic cells. That means your body cells. All right, so now we're moving oxygen from a level of high concentration in the bloodstream to an area of low concentration in your cells. It is unloaded from hemoglobin and it diffuses out into those cells and tissues to be used to make ATP. Likewise, carbon dioxide is going to be moved into your bloodstream, and you may recognize this equation. We know the number one method for transport of CO2 is as the bicarbonate ion. That's the most common method for transport. All right, so just to kind of summarize what's found on the bottom of page 77, oxygen transport, you'll see 98% of oxygen is transported as hemoglobin. That means the vast majority of our oxygen is bound to hemoglobin on those red blood cells. Just a very small portion at 2% is found dissolved in blood plasma. Just a reminder that oxygen and hemoglobin have an affinity for each other. Do you recall what that means? The word affinity. That means that oxygen likes to bind with the iron molecule on these heme groups. You may recall there are 4 of them. And that means we can bind up to 4 oxygens on a hemoglobin molecule. We also talked about back in an earlier chapter that if you have 4 oxygens bound, we would say that's 100% saturation of a hemoglobin molecule. If you only have 3 oxygens bound, that would be what percent? 75% saturation. That is basically what we're looking at here is 75% saturation at all times. That way you always carry a reserve supply on your hemoglobin molecule. You'll notice in this quick animation, the shape of a hemoglobin actually changes configuration or shape, and that allows for those 4 total oxygens to be transported by hemoglobin. So we know that oxyhemoglobin is when oxygen is bound to the hemoglobin molecule. Deoxyhemoglobin is what happens when we unload during internal respiration. Okay, so if you will flip on over with me to page 79, we are now going to talk about the oxygen-hemoglobin dissociation curve. So first of all, let me give you some background information. We know that oxygen has an affinity for hemoglobin, or likewise vice versa. And that has to do with this S-shaped curve here. Instead of being just a straight line, you'll notice it gently tapers off up toward the 100% range of saturation, and that's because we're looking at an affinity for oxygen and hemoglobin for each other. All right, this is the x-axis running across the horizontal portion of your graph. You'll notice it is P with a little a and an O2. That stands for partial pressure. That's what that P is. It may be a big P, it may be a little p. I know that sounds like Sesame Street. The A stands for arterial. So partial pressure in an arterial of oxygen gas. So PaO2 measured in millimeters mercury pressure. All right, and of course we know that 80 and above is ideal. That's what we would really like. And that we know 60 is a critical number because that means we're at hypoxia. So we really want to avoid falling lower than 60. All right, from 0 to 100% on this y-axis, that's this one here, we're going to look at hemoglobin saturation. So when we're talking about this y-axis, you will notice we run from 0 to 100%. At 25%, that means we have one oxygen molecule bound to a hemoglobin. At 50%, we have two oxygen molecules bound. At 75%, we have three oxygen molecules bound, and of course, 100% would be four total oxygen molecules bound to a hemoglobin. So let's talk about normal. This normal line here is in the very center, and it represents what happens at low levels of oxygen saturation versus what we have down here, which is arterial oxygen pressure. You'll notice that there are two dotted lines. We say the dotted line to the right of the solid line in the center is a shift to the right. Okay, so that's a shift to the right. This one is a shift to the left. You'll notice some things here that can influence which way we shift this line. We've got CO2, temperature, and pH that can shift you either to the right or to the left. Let's focus on the right shift first. Shift to the right prompts oxygen to dissociate or unbind from hemoglobin more readily. That decreases saturation. Where's the oxygen going? Cells. What's it doing there? It's going to make ATP. So let's think about this. If you're exercising and you're getting warmer as you exercise, there's increased temperature. You are increasing your hydrogen ion concentration due to acidosis, perhaps through exercise. There's that decreased pH. And of course, during exercise, we burn off more ATP. That can create more CO2. So exercise would be a great example of what would cause a shift to the right. That means oxygen is willing to break up with hemoglobin and move out into those cells and tissues. So really, this chart here predicts whether or not oxygen is going to stay together with hemoglobin or whether it's going to break up from hemoglobin. So let's talk about a shift to the left. Again, CO2, temperature, and pH levels can influence a shift to the left. This is more like a case of rest. So if you're resting, then you may get cold as you sit still. You may go into alkalosis, and your CO2 levels may decrease. At any rate, any of those three things can cause this graph to shift to the left. So let's get to a clean picture and we'll talk a little more. So let's say that we have 60 as our partial pressure of oxygen. You're going to follow that line up here. And if you come to the regular solid line in the middle, you'll notice that gives us a saturation somewhere, looks like, let's just say 86%. So that's at least 3 oxygens bound to a hemoglobin. Okay, I'm just going to put a circle right there. Let's say that you are outside working, exercising on a hot day. That's going to increase the temperature. Well, that will shift us to the right. That's that red dotted line to the right. Start with 60, come back up, but this time stop at that dotted line. When you come across, you'll notice that we've dropped. Let's say that's somewhere around 82%. So we have decreased the saturation. What happened to all that oxygen? Oxygen diffuses to your cells and tissues. And what for? To make ATP. Okay, so we say that when you have these three conditions, acidosis, don't worry about DPG, increased temperature or increased CO2, you're looking at a shift to the right. Let's talk about the same number. Let's say that you're at 60 millimeters mercury. This time, let's say that you're cold. Notice this time we're going to shift to that left dotted line. Let's draw a line across. Let's say that puts us at 92%. Okay, so now we say we've increased saturation because we've got more oxygens bound to the hemoglobin. Cold temperatures, increased pH, which is alkalosis, or we can look at decreased CO2, all being causes for a shift to the left. So where does this come into practical application? When people undergo surgery, they will decrease their temperatures. Why do that? Well, if you decrease temperature, what have you done to the saturation of oxygen on hemoglobin molecules? You've increased it. What does that mean about your respiratory system having to work to bring in more oxygen? Doesn't have to work as hard. Okay, so if you put people through surgery and you cranked up the temperature in the room, then their bodies would have to work harder to bring in more oxygen and distribute that oxygen to our cells and tissues. If you've heard about people falling through frozen lakes in the winter and surviving, this is the science behind it. So if you happen to be really cold really quick, then oxygen stays bound to hemoglobin. It circulates closer to your vital organs, possibly keeping you alive longer. So let's take a moment to look at an example here using 30 as our number. Predict the percent saturation if you have a normal body temperature. Okay, that's going to be 56% saturation. That's going to be normal. Now, using that same number, 30, as our millimeters of mercury, predict the percent saturation if you have someone who is exercising and hot. This time, you shift to the right. That means you're going to use the red line here. And if you go across, you're going to find that you're at 43% saturation. Where'd all the O2 go? It goes out into the cells and tissues. What could predict a shift to the left? Well, you're looking at cold temperatures, CO2 changes, or hydrogen ion changes. And so that means that we have an increased saturation as much as up to 69%. So what predicts a shift to the left or the right ultimately lies on blood chemistry and body temperature. Okay, just another look. On the test, you will want to feel comfortable being able to take a partial pressure, read the lines based on normal or abnormal conditions, and then determine a percent saturation. So this one we would predict for normal would be something like 83%. All right, so that takes us over to the last page of information, which is going to be page 80, carbon monoxide and hemoglobin. Carbon monoxide binds irreversibly with hemoglobin, which is actually different than oxygen. Oxygen binds reversibly with the iron molecules on hemoglobin. So the problem is once carbon monoxide binds, it's difficult to force off, and you need high pressure of oxygen, which can be provided by nasal cannula or hyperbaric chambers to force the carbon monoxide off the hemoglobin, allowing oxygen to then be transported. All right, so we have covered in this session a set on external respiration and a set on internal respiration. This is probably the toughest part of this chapter.